Hello, everyone. So let's continue with polynomials. If we have extra time, I'm going to review a little bit about things we had before. Maybe some number theory and some parts of the first chapters of the book. So let's start. So we got to this point that if we have, so we saw if we have, say R of X, polynomials over R, we can fix a polynomial like f of X. And then we can study polynomials. We can look at polynomials mod f. So just like what we had for natural or integers, for example, we used to say, I don't know, 5 mod 3 is equal to 2. So it means 3 divides 5 minus 2. That's the case for, same thing holds for polynomials. So if we have two polynomials, R of X and S of X, we say they are equal mod f, or they're equivalent mod f, a polynomial f of x, if f of x as a polynomial divides r of x times s of x. Which means if we divide r of x sx, if we divide it by f, it would be f of x times another polynomial q of x plus the remainder is going to be 0. What do you mean by lecture PDF? Are you referring to my PDF? I didn't upload any PDF for today. Or you're referring to a PDF Onhei has uploaded. Okay, type here, I would read that. So, okay. So, so that would be, that's, I would also check that, okay? When you're thinking about the question, I would go and check it. So that's what we mean. That's what we mean by two polynomials to be congruent mod another polynomial. Okay. So for example, suppose we are thinking about polynomials over R of X, and we choose the polynomial f of x to be x squared minus 1. Okay. So I want to study congruence classes mod f. So let's go to a new page. So we have R of x. It is the set of polynomials with coefficients in R. And we take f of x to be x squared minus 1. And the question is, what are all the congruence classes mod f? So this question is very similar to, say, the similar question about integers. So previously in number theory, we were thinking about integers. And if I fix a number, if I study integers mod, say 5, I could ask you what are the congruence classes mod 5. And the answer is 0, 1, 2, 3, 4. These are congruence classes mod 5. Any other number is congruent to one of these numbers mod 5, right? Now the same thing is correct for polynomials. When we have a polynomial, like here, f of x equals x squared minus 1, we can ask what are the congruence classes mod this polynomial, f of x. Now the point is that here, in about integers, I can always assume these numbers are less than 5 and greater or equal than 0, right? Because if they are greater than 5, say if you take 7, 7 mod 5 is the same as 2. So we can always change them, reduce 7 to 2, something which is less than 5. That's kind of the case here. When we are studying congruence classes mod a polynomial like f, similar thing is to say degree of these polynomials is greater or equal than 0, and it's less than degree of f. What are you talking about? Oh, I see. I would ask her about the PDF. Okay, so degree of these polynomials we are studying, we can assume it's greater or equal than 0 and it's less than degree of f. Okay, so here the degree of f is 2, right? The way to solve this problem is like this. Therefore, the answer is this. We should say degree of f is 2. So when we are studying, when we want to list all congruence classes mod f, their degree should be greater or equal than 0 and less than 2. So that's the first step. So degree should be less than 2, so the degree also either should be 0 or the degree should be 1. Okay? Now, if degree is 0, what does it mean for a polynomial to have degree 0? It means it's just a constant number, right? Constant number. You know that, right? For example, when we have, if a polynomial g of x is equal to, I don't know, 3, just a number, no x, we say degree of this polynomial is 0. Degree of g of x is 0. Okay, so that's either the degree is 0, which means it's a constant function, constant polynomial, or the degree is 1. If the degree is 1, it means that polynomial would look like something like this, ax plus b. So if the degree is 0, the function would be just a constant number, say c. And so that's it. These are all congruence classes. So the congruence classes are either of the form ax plus b, or they are of the form c, where here a, b, and c are real numbers. Okay, any question here? Is it clear? So we were supposed to list all the congruence classes mod f, where f is x squared minus 1. I said just like the case of integers, where, for example, when we wanted to see what are all numbers mod 5, the answer was 0, 1, 2, 3, 4, which means we're assuming these numbers are they're greater or equal than 0 and less than 5. Here, the similar thing is the congruence classes are the classes of functions. We can take functions which the degree is greater or equal than 0 and is less than degree of f. And here the degree of f is 2. So we should look at the polynomials which their degree is greater or equal than 0 and it's less than 2. So either the degree is 0 or the degree is 1. There are two cases. If the degree is 0, it means the polynomial is just a constant number. If the degree is 1, it means the polynomial is of the form ax plus b. So these are the set of all congruence classes mod f. Any question? Okay, so let's continue. Now, there is a kind of a problem with this polynomial f of x equals x squared minus 1. And the problem is kind of similar to the case of, say, Z4. Consider Z4, this is the set of numbers 0, 1, 2, and 3, right? Here, 2 is a non-zero number. 2 is also a non-zero number. if I multiply these two numbers, I would get 4, which here in Z4, it is equal to 0, right? So multiplication of two non-zero numbers is equal to 0 here, became 0. The same thing happens here. If we take x minus 1, if we look at the set of polynomials Rx, mod x minus 1, mod this polynomial, x squared minus 1, I'm sorry. Here, x minus 1 is a non-trivial polynomial. It's a polynomial which it's not 0. X plus 1 is another polynomial which it's not 0. But if I multiply these two polynomials, I would get x squared minus 1. But x squared minus 1 mod x squared minus 1, mod x squared minus 1 is 0. Because obviously, well, remember, these two things, they are equal, mod x squared plus 1 minus 1, if this polynomial here, which is x squared minus 1, divides their difference, which is x squared minus 1 minus 0. And that is trivially correct. Any polynomial divides itself. So we have two non-trivial polynomials, but their multiplication is 0. Now, if you remember from the case of integers, this thing that the multiplication of two non-zero numbers becomes 0 doesn't happen in Zn if n is, so this doesn't happen. This doesn't happen in Zn if n is, does anyone remember what is the condition we need on n? So we wouldn't have any 0 divisor.
Is it invertible?
Well, n as an integer. N is just an integer. It's like 2, 3, 4, 5, 6, 7.
What Tori said, because she's always right.
Yeah. So if it's prime. So here 4 is not prime. This thing, so these numbers are called 0 divisors. 0 divisor means the number is not equal to 0, like 2 here. But I can multiply it with another non-zero number, here again 2, such that their multiplication becomes 0. Here 4 is really equal to 0 in Z4. So another example is Z6. For example, in Z6, 2 is not 0, 3 is not 0. But if I multiply them, I would get 6. In Z6, 6 is equal to 0. Because we are considering everything mod 6. Okay, these are called 0 divisor. So the condition here we want is that when we are studying numbers mod n, this n should be prime. Now, there is a similar story here for polynomials. If we are considering functions, here the functions are Rx. Polynomials. Mod another polynomial f of x, we don't like this thing to happen. We don't like to have non-zero polynomials like x minus 1 and x plus 1, such that if we multiply them, we would get a polynomial which is equal to 0. We don't like that. And it's kind of similar. F in some sense should be prime. Actually, the word we use here is irreducible, which means we shouldn't be able to decompose f any further. We shouldn't be able to write f as multiplication of two other polynomials, which those things are not invertible. Here, x squared minus 1 is reducible in the sense that we can decompose it into, well, x minus 1 times x plus 1. Okay, so let's look at an example. So Well, so x squared minus 1 is reducible in Rx because we can write it as x minus 1 times x plus 1. What about x squared plus 1? Is it reducible or irreducible? So reducible means we can factor it or we can decompose it. Irreducible means we can't decompose it. So in R of x, can we decompose this thing to simpler polynomials? Is it possible? Yes, you're right. So we can't do it in R of x. In R of x, there is no way to kind of simplify this thing as multiplication of two other polynomials because it's simply yes, because it doesn't have any roots in R. But what about in C? Can we decompose it in C? Is it possible to write this polynomial as multiplication of two other polynomials in C? Well, these things should, yes. Can you tell me that the answer is yes, it is correct. It is reducible. Can you tell me what are those polynomials? You can just unmute yourself whenever you want to give an answer. It's fine.
Plus minus I.
Yes, that is correct. Yeah, so here we have x minus I times x plus I. If you do this multiplication, you can see we get x times x, which is x squared, x times I, which is ix, minus I times x, which is minus ix, minus I times I, minus I times I. But I times I is I squared, which is minus 1. There is another minus 1 here. It's going to be minus 1. It's just plus 1. Well, ix cancels with minus ix. What remains is x squared plus 1. So being reducible and irreducible depends on like the ring and the field we are studying this thing there. Okay. So this thing is irreducible over R, but it is reducible over C. Now there's an interesting theorem. So for example, say we are considering these things mod, say Z nx or Rx. There's an interesting thing. So there are two things to consider. One is greatest common divisor of two polynomials, which I talked a little bit about in the previous meeting. The other one is the fact that we can compute the inverse of polynomials. So if you have a polynomial, we can compute its inverse. Okay, let me explain what do I mean by that. So again, consider say, consider Z2. Z2 is the set of only two numbers, 0 and 1, okay? And then consider Z2x. This is the set of polynomials where the coefficients are only 0 or 2. So for example, x squared plus x cubed plus 1, etc. These are the polynomials here. The coefficients can only be 0 and 1. Okay, the coefficients always come from here. And because Z2 has 0 and 1, the coefficients can be only 0 and 1. Okay, so consider this polynomial here, x squared plus 1. First of all, on Z2x, is this polynomial is f reducible or irreducible? Can we decompose f into like other terms, simpler things, or we can't? Think about it for a few minutes to see if we can decompose it or we can't on Z2. Okay, no. Why is that? Does this thing have any roots? Let's see. Okay, so let's see. Well, you shouldn't think about I anymore because we are not in C. I understand your argument. You're saying you already have a decomposition, but that decomposition is not valid in Z2, x minus I times x plus I. But the point is that there might be completely different decomposition here, which doesn't have anything to do with I. So let's see, first of all, if f has any root here or not. What is f of 0? F of 0 is 0 squared plus 1, which is 1. And this is not 0. So 0 is not a root. What about f of 1? It's going to be 1 squared plus 1, which is 1 plus 1. But in Z2, 1 plus 1, which is 2, is actually 0. So 1 is a root of this polynomial. Okay? So x squared plus 1 potentially can be written as x minus 1 times something else. What is that something else? X minus 1. Okay, let's see. So x minus 1 times x minus 1 is x minus 1 squared, which is the same as x squared minus x minus x. Minus 1 times minus 1 is plus 1. This is equal to x squared minus 2x plus 1. But what is minus 2x? We are in Z2. Minus 2 in Z2 is the same as 0. Remember, Z2 has only two elements, 0 and 1. So all even numbers mod 2 are 0. So this is just 0. So this thing is 0. So what remains is x squared plus 1. So actually here, x squared plus 1 is irreducible, and we can decompose it. But we could see that slightly even easier. So on Z2, minus 1 is equal to plus 1. Do you agree? Well, because minus 1 mod 2 is the same as minus 1 plus 2, which is 1. Yeah. So x squared minus 1 is the same as x squared plus 1, because minus 1 and plus 1 are the same. I asked you to decompose this one, but you could say these two are equal. And then you can see x squared minus 1 can be written as x minus 1 times x plus 1. But again, it really doesn't matter if we write x plus 1 or x minus 1, because minus 1 and plus 1 are equal here. So here x minus 1 is equal to x plus 1. So it's just multiplication of x plus 1 by itself, or x plus 1 by x minus 1. So it is reducible. Let's look at another example. Let's consider, again, on Z2. Let's consider this polynomial, f of x equal x cubed plus x plus 1. Is it reducible or irreducible? Okay, think about this one for a few minutes. Does anyone have any answer? Yes, that is correct. So the idea is that whenever we are working with Z2, or in more general case, Zn, we should always try all these numbers here in Zn. In our case, it's Z2, and we only have 0 and 1, to see if f is 0 at any of these points or not. So f of 0 is going to be 0 cubed plus 0 plus 1, which is 1, and 1 is not 0. F of 1 is going to be 1 cubed plus 1 plus 1, which is 3. Mod 2 is 1, and 1 is not 0. So f doesn't have any 0. So if f doesn't have any 0, f can't be reducible here. Why? Because f is something with degree 3. The degree here is 3, right? Degree is equal to 3. If I decompose it as multiplication of two things, degree of one of them has to be 2, and degree of the other one has to be 1, right? And anything with degree 1 has a root. So for example, here, degree 1 should be something like x minus 1 or x minus 0, which is just x, right? So, and then 0 and 1 would be the roots here, so it should have some 0. But because f doesn't have any 0, it means this polynomial here is irreducible. Okay, so whenever we are thinking about polynomials being reducible or irreducible over Zn, like here Z2, we should try all the numbers here to see if f is 0 at any of these points or not. Now, in Z2 of x, this polynomial is irreducible. F of x equals x cubed plus x plus 1. Okay. So I want to compute inverse of a polynomial mod f of x. So consider g of x equal x squared plus 1. I'm looking for inverse of g. By inverse of g, I mean another polynomial such that if you multiply, well, this earlier I said over Rx, or sorry, Znx, it only makes sense over Znx. I'm sorry, it doesn't make sense over Rx. G inverse is another polynomial such that if I multiply g of x and g inverse of x, mod f, this is going to be 1. So let me give you an example. Here, x squared plus 1, I claim there exists another polynomial such that if we multiply these two, mod f of x, the answer is going to be 1. That other polynomial here is x. You can just check. X squared times x is going to be x cubed. 1 times x is x. Now, this equality is correct. X cubed plus x mod f of x is equal to 1. Why? We know this is correct if f of x divide x cubed plus x minus 1. Is it correct or not? If it's correct, tell me why. Does this polynomial divide this polynomial? That's the question. They look very similar, but one of them has plus 1, the other one has minus 1. Is plus 1 and minus 1, are they different here? Remember, we are in Z2. In Z2, plus 1 is the same as minus 1. So here, minus 1 is actually equal to plus 1. Therefore, Well, this is the same as f of x, and any polynomial divides itself. So it simply means x squared plus 1 times x mod f is equal to 1, mod f of x. It means x squared plus 1, its inverse is equal to x, because x is the thing which if you multiply x squared plus 1 by that, you would get 1. Let's compute some examples of this thing. Now, for example, consider z3 of x. It means polynomials which their coefficients are 0, 1, and 2. The coefficients are coming from z3, okay? And take f of x to be x cubed plus 2x plus 1. So first question, is f reducible? Again, in order to answer this question, I want to understand if this polynomial is reducible or not. I should try to plug in all these numbers into f and see if I would get any 0 or not. F of 0 is equal to 0 cubed plus 2 times 0 plus 1, which is 1. And 1 is not 0. F of 1 is equal to 1 cubed plus 2 times 1 plus 1. It's 1 plus 2 plus 1. It's 4. 4 mod 3, here we are in Z3. 4 mod 3 is 1, and 1 is not 0. So 1 is not a root either. What about 2? F of 2 is equal to 2 cubed plus 2 times 2 plus 1. This is 8 plus 4 plus 1. It's equal to 13. Mod 3, 13 is the same as 1. The remainder of division of 13 by 3 is 1. And 1 is not 0. So f has no 0. And the degree of f is 3. It shows f is irreducible. F is irreducible. Okay. Okay, so this function f of x is irreducible. Now, let me erase some of these. So we are in Z3 of x, and f of x equals x cubed plus 2x plus 1 is irreducible. Now consider another polynomial. Let's say gx equals x squared plus 1. The question is to find, I want to find the inverse of this x squared plus 1. The inverse of x squared plus 1 mod f, which means I want to find another polynomial like h of x such that if I multiply gx by that, the answer is 1 mod f. Does this question make sense to everyone? I want to make sure you are not confused. You are following what is the question about. So I have a polynomial f, which is irreducible. I am given a function g of x, x squared plus 1. I'm looking for its inverse. Inverse means another polynomials like h, such that if I multiply g by that polynomial, the result is equal to 1 mod f. Okay? Now the way to do it is, so the algorithm to do it is to start by dividing f by g. So first step is divide f by g. Here f is x cubed plus 2x plus 1. Let's divide it by g, x squared plus 1. Okay, here I have x cubed, here I have x squared, so I should write x here. I would get x cubed plus x times 1, which is just x. I should change the signs. X cubed minus x cubed, they cancel. 2x minus x is x. There is plus 1 here. I would write it here. Now, here the degree is 1. Here the degree is 2. Whenever the degree here is less than the degree here, we should stop. Now, 1 is less than 2, so we should stop. So we divided x cubed plus 2x plus 1 by x squared plus 1. So x squared plus 1 times x plus 1 is equal to x cubed plus 2x plus 1. Okay. The next step is to divide g of x. I should bring this polynomial here. And I should divide it by this polynomial. So that would be the next step. The next step is dividing x squared plus 1 by x plus 1. Okay, here I have x squared. Here I have x. If I multiply it by x, I would get x times x, which is x squared. X by 1 is x. I change the signs. X squared cancels with x squared. I would get minus x plus 1. But there is something to note. If in Z3, we are in Z3, right? Minus 1 in Z3, I would write it here. Minus 1 in Z3 is the same as 2. So rather than minus x, I'm allowed to write plus 2x. Now here, if I multiply x plus 1 by 2, 2 times x gives me 2x, 2 times 1 gives me 2. If I change the signs, 2x cancels with 2x, 1 minus 2 is going to be minus 1. Again, minus 1 mod 3 is the same as 2. So rather than minus 1, I can write plus 2. Okay, so x squared plus 1 divided by x plus 1 is going to be, it's going to be x plus 1 times x plus 2 plus 2. Okay. And finally, I should bring x plus 1 here and divide it by 2. Okay, let me erase this thing and write it here. So I am finally dividing x plus 1. I am dividing it by 2. Okay, what is the answer? Can anyone tell me what should I write here? What is the first thing to multiply to get x? No, you know, it should be 0.5 is not in Z3. Remember, the coefficients always should come from here. You're almost right in a sense, but not exactly. What if I write 2x? What I'm going to get? I'm going to get 4x. The final might be tough. I don't know. I even don't know what is the format of the final actually. But anyway, so what if I write 2x here? I'm going to get 2x times 2, which is 4x, right? But what is 4x? What is 4? 4 mod 3 is actually just 1. Do you all agree? Do you understand what I'm saying? So what I'm saying is that here I'm dividing x plus 1 by 2. I want to multiply 2 by something that would cancel x. First, it seems to be impossible, but if I multiply it by 2x, I'm going to get 4x. But I should remember, we are working in Z3, and in Z3, 4 is the same as 1. So 4x is actually just x, because 4 is the same as 1. And then I should change the sign. X and x, they cancel each other. 1 comes here. What now? The point is that I should still continue the division. I should multiply 2 by something to cancel 1. What is the number that if I multiply 2 by that number, it would cancel 1? Does anyone know the answer? By last, you mean x plus 1 by 2, or you mean the one I erased? Okay, yeah. So let me erase and write it again one more time. Maybe it helps. I want to divide x plus 1 by 2. So I should multiply 2 by something that I can cancel this x. That was always the idea in division, right? We always want to multiply the number here by something so we can cancel the term with the largest degree here. I said it seems first impossible because, as you mentioned, the answer should be something like 1 over 2x. So when you multiply 2 by 1 over 2x, you would get x. And then when you change the sign, you say they cancel each other. But I said 1 over 2, in some sense, 1 over 2 is not in Z3. But in another sense, it's correct because, well, the inverse of 2 in Z3 is really 2, which means if I multiply 2 by 2x, I would get 4x. And in Z3, 4 is equivalent to 1. So 4x is equal to just 1x. So 4 is equal to 1, so I can erase 4 and just write 1x. And when I change the sign, x and minus x, they cancel each other, and only 1 remains. Now I want to multiply 2 by something else such that it can cancel this 1 here. And the answer is again 2. If I multiply 2 by 2, I would get 4. But again, 4 is the same as 1. In Z3, 4 is equal to 1. So I can erase 4 and I can write 1. And then in the next step, I change the sign and they cancel each other. So x plus 1 is equal to 2 times 2x plus 2 plus 0. I know it looks very confusing to you, this division, because it's in Z3, but that's how it works. Yeah, it's a little confusing. And now I claim we have, let me erase this thing. Now I claim we have the kind of inverse. Let me erase these. We don't need these things anymore. Okay. So, so this is equal to 2 times 2x, which is 4x, plus 2 times 2, which is 4. But 4 is equal to 1 in Z3, so it's just 1x plus 1. Okay. Now the idea is to go back. Here, look at 1. 1 is equal, from here, is equal to x plus 1, obviously, minus 1, minus x. This is the last part, the last section of the book. It might be a little bit hard for you. If it is, you should review that section more carefully. And then you can ask me questions. So I can write it like that. Okay, how does it help now? So, you know, we are going kind of backwards. Maybe we should practice this thing more before continuing. So I'm not convinced that you really understood this thing. So let's try another similar example before going further. Let's consider Z2. Maybe Z2 might be easier. Consider Z2 of X. Suppose f of X is X to the 4 plus X plus 1. Let's just do this Euclid algorithm again. And suppose G of X is X squared plus 1. Suppose I want to find greatest common divisor of these two polynomials. Okay, in order to do that, I should follow this algorithm I told you. First, I should divide f of x by g of x. I should do this division. Okay, so let's do it. It's x to the 4 plus x plus 1 divided by x squared plus 1. Okay, here I have x to the 4, here I have x squared. If I multiply x squared by x squared, I would get x to the 4. If I multiply x squared by 1, I would get x squared. I should change the signs. X to the 4 cancels x to the 4, so I would get minus x squared, and what remains is plus x plus 1. What should I multiply x squared with? Well, minus 1 in this case. I'm going to get minus x squared minus 1. Actually, the signs don't matter on Z2. I'm just repeating the same thing as before so it wouldn't confuse you. I should change signs. These two cancels each other. So what remains is x plus 1, which is plus 2. But 2 on Z2 is 0. So rather than 2, I can just write 0. So it means x to the 4 plus x plus 1 is equal to x squared plus 1 times x squared minus 1 plus x. In Euclid algorithm, why didn't you switch minus x squared? Where do you mean? You mean why didn't I change the sign? Yeah. So yeah, I got minus x squared, but I mean, it doesn't matter. I just mentioned that these two things are equal because minus 1 is equal to 1. It's in Z2, you are allowed to write minus 1, but you should just have in mind that minus 1 is the same as 1. So I switch it, but I have in mind that these two things are equal. It really doesn't matter. I'm allowed to write it. Like I can write 3 in Z2, but 3 is the same as 1. So whenever I have 3, I can just write 1. Okay, so yeah. I just changed it at the end. Yeah. So the next step means, the next step is dividing this x squared plus 1 by x. I should divide that. So let me erase this. I should do another division. So we have x squared plus 1. We want to divide it by x. Well, x times x is x squared. I change the sign. They cancel each other. I would get 1. So x squared plus 1 is x times x plus 1, which is kind of trivial. The next step is we should divide x by 1. Well, 1 times x is x plus 0. When we get to 0, we are done. We should look at the number exactly above 0. That's the greatest common divisor, which is 1 here. So the greatest common divisor of f and g is 1. Yeah, so, well, that's how it works. Let's see what I want to say. Okay, so let me just add this thing as the final thing I wanted to say in the previous question. Let me say it now. Here 1 is equal to x squared plus 1 minus x times x, right? Here 1 is equal to x squared plus 1 minus, if I take this x times x to the other side. Let's keep x squared plus 1 minus x times, rather than x, I replace x by what I have here. See, if you look at this equation, the equation circled with blue, x is equal to x to the 4 plus x plus 1 minus, I should take this thing to the other side, x squared plus 1 times x squared minus 1, right? So it is equal to x squared plus 1 minus x times this thing minus x times the second thing, which is plus x times x squared plus 1 times x squared minus 1. Now, here I have x squared plus 1 times, there is 1 x squared plus 1 here. There is x times x squared minus 1 times x squared plus 1 there, which is x cubed minus x. And then I have minus x times x squared plus x plus 1. Now, finally, when we get to this point, let me erase. It's the final step. I'm sorry that it took so long. It's the final step. So finally, it means 1. If you look at what we have here, 1 is equal to x squared plus 1 times x cubed minus x, which is the same as plus x plus 1, minus again, which in Z2 is the same as plus x times x squared plus x plus 1, right? Now, if I look at everything mod f, because what I have here, sorry, this is x to the 4. Because what I have, and this is also x to the 4, because this thing is equal to f, this is 0 mod f. So 1 mod f is equal to x squared plus 1 times x cubed plus x plus 1. So this thing here is the inverse of x squared plus 1. So I found inverse of x squared plus 1. So x squared plus 1 inverse is what? Which if you multiply x squared plus 1 by that, you would get 1. This is exactly that thing. I'm multiplying x squared plus 1 by this polynomial and I get 1. So guys, I know it might be a little bit confusing, especially because we didn't have like kind of our classes were all through Zoom. I guess it wasn't, and we had longer break, probably there wasn't enough time to go over this section, which is almost the last chapter and section of the book. So I know it might be confusing and a little bit hard. So I think you can review this chapter more carefully and try to solve the questions, and then send me an email. We can even like manage Zoom meetings to like speak about these questions more carefully and make sure you understand, because there are some difficulties here and I know it might be a little bit hard. So if you have any question, just ask me now, and probably would be very good if you review it more carefully and ask me your questions maybe today or tomorrow, whenever it's good for you. Okay, is there any question now? Let me see. Well, I'm not sure if there is going to be a review session. I would ask Onhe to make sure if there is. I'm not still aware of that. But if you really have questions, we can fix a time and it would be fine with me. We can have a review session. Yeah, I can do that. Yeah. Okay. Okay, so stay safe and goodbye.